Today we are going to discuss some of the important system calls in Linux and C which are related to operating systems and interprocess communication. Of them, the most important one is fork system call. System calls among that, one of the most important one is the fork system call. Fork system call. Number one. And regarding this fork system call, as you know, you have a program or process in execution. This is the program, and this is having a code area. Then data area is there. Then also stack area, and for some other purpose stack area is also there. This is a program in execution. This is a process. This is a process or a program in execution, and this is in the main memory of the computer. So when fork is called, what will happen? This fork is carrying no parameters. The fork system call does not have any parameters, and it will return an integer value. That means the method signature is like this: int fork without any parameters. This is the fork system call as far as C language is concerned. And when you are calling this fork, what will happen? So here this is a process, and in this process you have, say, in between, so in process ID and PID is equal to fork. That means here we have a set of statements, after that we have a set of statements, and this is process, or this is the parent process. This is the parent process, and this starts executing execution from its first statement, and it is having a number of statements like this. This is the code area. This is the code area, and apart from this, you have a stack area. And here for this another, suppose that this is the data area, this is the data area, and this is the code area, and the code is executed, and into PID means process ID is there, and that process ID and PID is equal to fork. When this fork system call is called, what will happen? This parent process, this is, as I told you, this is the parent process, and this parent process will create a new child process which is an exact replica of this parent process. That means up to this point only one path of execution. That means up to this point you have a single path of execution, and when PID is equal to 4, you have two processes are created, and this is the parent process and this is the child process. When fork is called, after this point you have two paths of execution. That means one is the parent and the other is child, and this is the parent, and child is also having, this is the data area and this is the stack area, and int PID equal to 4, exact replica of the parent process. Now here we have an int PID, and in Linux every process is having a process ID. A process is having process ID or PID, and PPID means parent process ID. This is the process ID, and this is parent process ID. Okay. Now this is the parent and this is the child. When you have executed this fork statement, it created two new processes, and not two processes, only a single new child process. The parent process as such is there, and this fork returns a number to this PID value. That means here after this fork statement, the parent PID, here we have an integer PID and that is residing in the data area, and in the this because this is a data, and in the data area you have a PID. Okay, and here also, here you have a PID in the data area, and when this is called, when this fork system is called, for a system call is called, at that point in time only parent was there, and upon executing that fork, it will create a new child process which is an exact replica of this, but only one difference. This fork returns, suppose that the child is having a process ID say 100, and parent process, this is the parent process, it is having say 99. Suppose that the process ID of the parent is 99, and if you are creating a new process, it is having another process ID that will be given by the operating system, and suppose that the process ID is 100, then the fork returns a value to process ID, and for the parent this will be 100. Why? The new child process which was created using this fork statement, and that child is having this process ID, and that is returned to the parent. That means this parent is having a process ID or PID value, child is also having a PID value. Those two are independent, but that means after forking or after creating a child process, this parent process and child process are exact replicas, but parent is having this PID and child is having another PID. That means the name is same, but separate data area, separate variables. This belongs to parent process and this belongs to the child process. And upon creating this, the child is assigned a process ID by the operating system, and that is returned to the parent. That means once this parent creates a child process, the fork system call returns the process ID of the child to its parent. That is returned by this fork statement. That means fork returns a value. Fork returns an integer value, but the returned value is not the same for both child and parent. In the parent process, this fork system call returns the process ID of the child. That is why you have PID is equal to 100. But in the child process, the ID returned is 0. PID is equal to 0. That means the only difference between the parent process and the child process is the process ID returned by fork. That means if fork returns in parent, fork returns the process ID of the child it has created, whereas in the child that will be 0. Okay, so that's all about fork. And when we are this is the life cycle. That means once you have a fork statement, this is the parent and this is the child. The use of this fork statement is, suppose that if you are doing some program and in between, suppose that if you want to execute some other program, that means you are executing a program and in between you want to execute some other program. So for that we are using
this fork. That means a separate thread of execution or separate execution path is generated. That means a new process is created, and that new process is useful, or that is used to execute some other program. Suppose that you have a program, say P1. P1 is a program and P2 is another program, and your program, that means these are the statements of the program. Suppose that at this point in time you want to execute this P2, want to execute P2. That means you have an executable code P1 and you are executing that, and in between you want to execute this P2. That means P2 is some other program, whether it is a system executable file or you can create your own executable. Okay. Suppose that you have P1.c and this is P2.c. You have compiled this P1.c as P1 and that is the executable code P1 and this is P2. Okay. Then what you can do is, at this point you want to execute this P2. So here at this point you have to give a fork system call. A fork system call is, here can have a fork system call. Here once you have a fork system call here, now you have two paths of execution, two paths. Once you have forked this, now this is the parent and this is the child. Okay, this is the child. And as I told you, here the parent process is having PID greater than 0. That means this, the process ID of the child will be a positive number. It cannot be a negative number, positive number, and that's why the PID of the parent will be greater than PID greater than 0. But for this child, PID is equal to 0. PID is equal to 0. Equal to 0. Then after this point, that means you are executing a program, and at this point you have 4, and now you have two parts of execution. That means child is executing a different one and parent is executing. That means those two processes are entirely different, but looking at this PID, process ID value, you can decide upon whether it is a parent or the child. Okay, that means if PID is equal to 0, that is the child, and if PID greater than 0, that is the parent. So I am going to write the code for that. That means you have a set of statements P1 dot C. This is the program, and here you have fork. You have fork. Now the next statement is, if PID greater than 0. If PID greater than 0, that means this is the parent. Now execute this. Else, if PID equal to 0. Let's say PID equal to 0, what will happen? You have to execute this. And after that, this is the, so here you have a set of statements for the execution of this. But now, as I told you, here I am going to execute program 2.c, or program 2.c. After compilation, you have P2, which is the executable code. You have compiled this P2.c to P2. And now after forking, you have a child process and a parent process, and using this child process you are going to execute this P2. So for that, what you can do is, you can, if PID greater than 0 something, that means say printf parent, this is the parent, and and if it is a child, what you can do is you have to execute this P2. For that, you can have another system code which is called exec system code, and here you have to specify the path, say /home/P2. So this is the path name you have to give. Okay, this is the path name, followed by some other attributes, some other parameters are also there. In general, you are going to execute this exec home/P2 means, now as I told you, here this is the child and this is the child. This child is going to execute this home/P2. So if you want to execute a program, you have to create a process and you have to load the entire program in the main memory of the computer. But here in this case, when this exec system call is called, what will happen? Then this code, that means this is P2 is the executable code. Now this child process is exact replica of the parent process. Data area, stack area, those are exact replica of the parent. Now when this exec system code is called, what will happen? When this exec system code is called, the entire content of this child or this process, that means if some process calls an exec function, and that means this area will be replaced by this memory area will be replaced by P2, and it starts execution from the start. That means you have created a child process which is an exact replica of the parent, and in the child process, if you are calling this exec function, what will happen? That means that the contents of this child is replaced by this P2. Now this P2 has code area, data, stack area, etc. there. That means that is loaded into the area reserved for child, and it starts execution from the start. And once it is completed, once the execution of this is completed, that will return, and here after this exec system code, here you can have an exit system code. That means here when this exit system code is called, control is returned. That means the child will be no more. And that child exits, and after that, when this exit system call is called, after that no more child process. That means this space is evacuated. Okay, that means once you have forked this, once you have a fork system call, then you have created a child process. Here this is the child process, and now this child process is calling the exec system code, and this is some other path, and once it is completed, then here you can have an exit system code, and for the completion of this child process, this parent is waiting using wait system code. That means when a wait system call is executed, it is waiting for the child to complete, and once this is exited, the control is given back to this wait, and this parent can proceed. Okay, this is very important as far as operating system calls are concerned, for exec, exit and wait. These are all related. Okay, so this is given. This is using in our experiment number 2. Okay, thank you.